Okay, well, we can get started. I told you it would be a big crowd.
No worries.
So it's a pleasure to have Raagini, student at Cornell with Nick Battaglia. She's going to tell us about her work on the kinetic Sunyaev-Zel'dovich effects.
Yeah. Okay. So hi everyone. Thanks for the intro. And yeah, if you have questions at any point, since it's a small group, just ask me and I can pause and explain. So yeah, I'm going to present about our recent paper, which we just submitted a few months ago, and in which we proposed a novel bispectrum to extract the KSC for to learn about cosmology using the KSC effect. So I can actually just change.
Okay, sorry.
Yeah, I don't know. Okay. So, okay, so a super quick intro to the KSC because everyone might not be working on it here. So, right. So the kinematic Sunyaev-Zel'dovich effect, or the KSC in short, is basically the Doppler boosting of CMB photons when they encounter free electrons in the intervening lattice structure as they travel towards us. So this picture here shows the actual inverse Compton scattering that happens between CMB photons and the free electrons that they meet in the intervening medium. And if the free electrons are moving with respect to the line of sight, then this basically induces a Doppler boosting in the CMB that we see in that patch of the sky. So the net effect of the KSC effect is that it induces a secondary fluctuation or anisotropy in the CMB that is proportional to the integrated electron momentum along that line of sight. So this is a key point here. The relative shift in the temperature is proportional to the electron momentum. So that's the electron density times its velocity with respect to the CMB rest frame. Okay, and the KSC effect starts dominating over the CMB at small scales, so above multiples of around 3,500 or 4,000, which means that the KSC effect becomes detectable when you have high resolution CMB data, which we now have from the Atacama Cosmology Telescope, or ACT, SPT, and the now the Simons Observatory, which has just started operations. So we will be getting good quality, high resolution CMB data from these telescopes. And because the KSC effect arises due to this motion of free electrons, and the motion along the line of sight is equally likely to be towards us or away from us, so the induced shift due to the KSC is equally likely to be positive or negative, depending on whether the free electrons are moving towards us or away from us along the line of sight. So this is another key point, that the KSC anisotropy is equally likely to be positive or negative. Now, why is the KSC effect cool, or why should we study the KSC effect? So as I mentioned earlier, the induced shift due to KSC is proportional to the electron momentum, which means that it gives you a handle on the gas density or baryonic density, which can tell you about the astrophysics of gas in the intervening large-scale structure. And from the velocity part of the induced anisotropies, we can also constrain cosmology using the KSC effect. So on the astrophysics side, the overall amplitude of KSC signals that can be measured from data can tell you about the abundance of baryons at different redshifts. And this has been previously used to address the missing baryon problem. And again, it can, by looking at the gas density as a density profile, it can also tell you about the distribution of baryons in the intervening large-scale structure that is being probed by the KSC effect. And on the cosmology side, peculiar velocities or the velocities that are in the above equation, they probe the largest scales in the universe. So in linear theory, velocities are given by this equation here, which just comes from the continuity equation. And velocities dominate at linear, very large scales. And this is really cool because then using the KZ effect, we get cosmological information on the largest possible scales that we can probe. And from this expression, we also see that velocities trace the total matter density in the universe, and they also the velocities are also proportional to the linear growth rate of large-scale structure, which is denoted by F in that expression. Now, through this dependence, the KSE effect can give you constraints on neutrino masses, dark energy, modified gravity models, and primordial non-causality. So it can have a lot of different cosmological implications through its dependence on the growth rate and the total matter density field. So that's why I think the KSE effect is super cool. And how do you actually detect the KSE in CMB data? So a key thing is that the KSE effect does not change the black body spectrum of primary CMB. So you cannot just isolate the KSE by component separation techniques the way you do for TSE. So what is often done is you combine CMB data with large-scale structure data, some kind of large-scale structure data, to detect the KSE that at those redshifts, basically. And I won't go into the details of all these different estimators for KSE. I'm just mentioning them here. So how you can combine CMB and large-scale structure data to detect the KSE? There are different statistical estimators in literature that have been proposed to do this. The first one was pairwise KSE, which yielded the first KSE detection back in 2012. And then these are two other methods which have also been used for measurements in ACT data. The velocity reconstruction method, the first measurements with this method were just released, were just done a few months ago in ACT data. But one thing to note is that all these different estimators are of the 3D tomography type. Basically, they are looking at the KSE effect in 3D, so also as a function of redshift. And all of them require individual redshifts of galaxies to extract the KSE. So that's one thing that's common in all of them. And then another paper has also shown that all of these different techniques to extract the KSE are mathematically equivalent to looking at a bispectrum of 1 power of temperature and 2 powers of galaxies. So in that sense, all of these estimators are equivalent. What I'm going to talk about today is the detecting the KSE effect using projected fields of large-scale structure tracers. So basically, I'm going to talk about a technique which does not require individual accurate redshifts for galaxies in order to extract the KSE effect. You only need a rough TNTZ or redshift distribution for your tracers, which means that this technique is applicable to photometric galaxy surveys, which might not have individual redshifts for each galaxy. So like the WISE galaxy sample. And we actually make forecasts using the WISE galaxy sample where you just have a rough redshift distribution. And interestingly, this technique, the same exact formalism, can also be used to any other large-scale structure tracer. So that could be quasars or CMB lensing convergence field, or even 21 centimeter fluctuations. And this has been explored in some other work, but yeah, basically this whole formalism is also applicable for these large-scale structure tracers. And
Excuse me.
yeah, go ahead.
So for 21 centimeter, aren't these, doesn't that usually have high spectral resolution? In which case, would you want to use this? Would you want to use a projected field for 21 centimeter?
So is your question more like, can you use the other techniques also with 21 centimeters?
Yeah.
So at least in the current form, the other techniques specifically use either spectroscopic galaxies, or you need to know the redshift of the galaxies accurately enough to do those sort of techniques. So
I guess those techniques specifically for galaxies where you have high
Yeah,
angular, well, you have high angular and high spectral resolution in order to find those galaxies.
yeah, like you know the redshifts of the galaxies pretty well.
But then you also need to
even
know the angular
resolution.
resolution really well as well.
Uh,
Did you have for galaxies versus 21 centimeter where the angular resolution isn't as good?
No, I don't think that's a concern. Like you need
Okay.
good angular resolution in your CMB maps because that's where your KC signal dominates.
Okay.
But on the large scale structure tracer side, you don't need very accurate, very high resolution in that.
Okay.
So yeah, I can actually come back to that later. But yeah, you don't need very high resolution in the large scale structure field.
Okay.
Yeah, you only need that in the CMB maps. And yeah, what I mean by projected fields of large scale structure tracers is we're going to look at, we're considering specifically in this world, field of a galaxy field that is projected along the line of sight. That's what I mean by projected fields. So that's exactly what this equation here is showing. You're projecting the galaxy field along the line of sight. But now, because you're using a projected field, if you just take the simple cross correlation of a clean CMB map, which has KSC in it, with this projected galaxy field, then statistically it's going to be 0 at most scales, or at least, yeah, at most scales. And that's because, as I mentioned earlier, the KSC is equally likely to be positive or negative along the line of sight. So if you just sum it together, it will cancel out and be statistically 0. So to avoid this like naive cancellation, what was done so far is, this is an existing estimator that I worked on in my previous paper, but the solution so far was to square the KSZ field or to square the CMB map before cross-correlating it with your projected galaxy field. And this sort of estimator is called the KSZ squared estimator. And so far there have been 2 measurements in Planck data using this technique with WISE and unWISE galaxies, and these were at the 3 to 4 sigma level. But in the future, the detection significance with this KSE squared estimator is expected to go up. So yeah, basically what has been done in this existing estimator is you take a clean CMB map, so a component separated clean CMB map. So essentially what you'll have is primary CMB plus KSE in your component. And then you Wiener filter it to select the KSE dominated small scales. Then you square it in real space, and then you cross-correlate with your projected galaxy field. That is what was done so far in the KSE squared estimator. But we noticed that this sort of technique has a bunch of drawbacks. One sort of straightforward drawback is that because you're squaring the CMB map in real space, once you go to Fourier space, that converts into a convolution of the underlying statistic. And because it's a convolution, it's going to mix up your information across different angular scales. And essentially what this estimator depends on, the underlying sort of theoretical statistic, is this bispectrum or 3-point function between 2 electron momenta and 1 density field. So the reason this comes up, the one that I've put in the square there, is because your KSZ is proportional to the electron momentum along the line of sight. You have 2 KSZ fields, so 2 electron momenta, and 1 density field from the last scale structure. So even though that's the underlying statistic, once you do this sort of a method, this estimator compresses the information contained in this 3-point function across different triangle shapes. So there is also some loss of information and mixing across different triangle shapes that happens with this estimator. In addition, it also picks up a significant contribution from CMB lensing that has to be accounted for. Now, moving on to the estimator that we proposed in this work, we again work with projected fields of large-scale structure tracers. So again, it's applicable to all the large-scale structure tracers that I mentioned earlier. We specifically did forecasts for photometric galaxies. And what you do in this is essentially you again start with a clean CMB map, and you just take the full 3-point cross correlation of 2 CMB fields and 1 projected density field in harmonic space. And the way you actually implement this is we chose to use the bin bispectrum formalism, which basically takes this 3-point function or bispectrum and it bins it in 3D harmonic space. And we do this for a bunch of reasons. One reason is simply that in any one triangle mode or for any given triplet of L1, L2, L3 that your bispectrum is a function of, the amount of signal in one single triplet is going to be pretty small. But if you bin it, if you do a 3D binning in harmonic space, then you still have much better scale separation than what was done earlier in the KC squared case. And because you're not doing that sort of a compression, we also get a much higher signal to noise ratio than the earlier method. And the weights that you're sort of seeing here, the N, when you do the spinning is just the number of triangle modes that you have for each particular triangle. So by a triangle mode, I mean, instead of having your signal as a function of a single multiple L, it's a function of 3 multiples, which form a closed triangle. So that's basically what we are doing here. And as I mentioned, you basically retrieve richer information across different triangle shapes, even though the underlying statistic remains the same. It's the bispectrum between 2 electron momenta and 1 density field. And also this sort of a scale separation, it also gives you better control over some modeling uncertainties. And I'll get to that. I'll get to that in a minute. As for the theoretical model of this bin bispectrum that we are looking at, this was actually based on my previous work for the KSC squared estimator, but it's applicable to both of these related estimators. So in my previous work, I basically derived an improved, more accurate model for this underlying bispectrum. And essentially, the theoretical model is a little complicated because your electron momentum P is density times velocity. So it essentially becomes a 5-point function. And in the end, you end up with 4 non-zero terms, which you add up together to give the final theoretical. This is just from perturbation theory, but this is just to say that the theoretical model has been improved in recent years, and it's reasonably accurate as of now. And it's also expected to be accurate across different triangle shapes, which is great because we need that in our estimator. And because this gets quite complicated, for the purpose of our forecasts, we used a fitting function for the matter bispectrum, and we sped this whole thing up with using emulators. And then we did forecasts for Simons Observatory or SO and CMB-S4, where we assume an Lmax of 8,000, so really small scales. And we did forecasts with WISE galaxies because that's what has been used before in previous measurements with the KSC squared estimator. And one thing we choose to do is we restrict the galaxy modes only to linear scales. So for the galaxy field, we put an Lmax of 700. And there's a few reasons for that, but basically once you restrict your galaxy field to linear scales, it's much easier to model it, and you avoid modeling uncertainties from like HOD modeling or non-linear galaxy biastroms and stuff like that. So the triangles that we are considering and where we actually find the most signal have this sort of a shape. In multiple space, in harmonic space, you have 2 KSD modes which are long or correspond to small physical scales. And you have 1 galaxy mode which is short or corresponding to linear scales.
So when geometric scaling is 0, does it mean that the term is 0?
Yeah, so actually, yeah. So that's basically because your velocities, again, are equally likely to be positive or negative.
Okay.
So those are just like parity odd terms. So overall, the term is expected to be 0. So in total, there would be 10 terms, but thankfully only 4 of them are non-zero.
Okay.
And this was also done in like a previous work, which I think I cited. Yeah, this was also explored in a previous work, but they did not include these 3 other terms. previously only the first term in the top row was included. We also calculated and included the 3 other non-zero terms.
Okay,
That's basically what I did.
yeah, I mean, like your second and third line look the same to me, but one is 0, the other is not, so I'm not sure what's the difference.
No, there's a prime on this third one.
It's
Right, but. I mean, you have.
yeah, so it's easier to show in the equation sort of,
Yeah.
but yeah,
Okay.
I can go into that later maybe.
Okay.
But yeah, it's different because even though it's like B delta delta,
Mhm.
the K mode that's inside is different. So
Okay.
I think yeah, so in the top one, if you look at the first factor, it's V of K times K1 minus K.
Mhm.
And in the bottom one, basically,
Oh, I see, it's the same K that shows.
yeah, if the same K shows up twice with like V delta, then it will become 0 basically.
And what is the mean redshift for the WISE galaxies?
So for the WISE galaxies that we did the forecast, I think it peaks at like redshift 0.3. But the spread is from redshift 0 to 1, and there's like a long tail from 0.3. But yeah, and that has we chose that because again, that doesn't have accurate redshifts for all the galaxies, but you can still apply it to such data.
But presumably you want to use this with LSST or something.
Yeah, eventually you could replace that with
Huge
LSST.
improvement.
Yeah, this is more to do sort of a comparison with the measurements that we already have with the old estimator. Because right now I think there's a group that's also doing the KSZ squared measurement with ACT data and WISE galaxies, or WISE or the unwise sample, which is also related. But yeah. But eventually, yes, you could use LSST galaxies. Right. So moving on to the forecasts. As I said, by default, we restrict the galaxy modes to an Lmax of 700 or just the linear regime. And we basically forecasted the detection significance of the signal as a function of your triangles. So we estimated the covariance assuming weak non-Gaussianity, and I can go more into that if there's questions, but basically, we forecasted the signal to noise ratio using the previous theoretical model and the covariance matrix, and we showed that the SNR peaks for squeezed triangles. We also explored what the signal to noise ratio would look like in the extended scenario, where we also include the nonlinear modes in the galaxy field. So this is like the extended regime, but most of our paper sticks to the Lmax of 700 and the galaxy mode, or yeah. But basically, even when we expand the regime in which we are looking at the signal to noise ratio, if we expand the galaxy modes up to an Lmax of like 4200, which is into the nonlinear regime for the galaxy modes, we still see that most of the signal is contained in these very squeezed triangles, which I showed earlier. Basically, your signal peaks for triangles which have a short large scale structure mode or short galaxy mode, and 2 long KSZ modes corresponding to small scales in the CMB. So even if we choose to restrict the galaxy mode to linear scales, you're not losing the highest signal triangles. And that's nice because you don't have the separation in triangle shapes if you just do the KSZ squared technique as earlier. And again, we don't have any convolution going on here because we don't need to use a Wiener filter. We are not squaring the CMB map in any place. So it's just a full 3-point function. So you have better separation of scales. And another sort of advantage that this estimator now has is that the lensing correction to this bispectrum signal is negligible in most of the bins. And yeah, earlier I forgot to mention, what I'm showing in the plots here is a slice for a fixed L1. So because your bispectrum is a function of L1, L2, L3, I'm showing slices in L2, L3 space for a fixed L1. And with this sort of a pattern that I'm showing here, we see this across different L1 slices, that most of the signal is in the squeezed triangles. And yeah, and the signal is higher when your CMB modes are high L, because that's where your KSE is dominating. So yeah, another advantage is that because the lensing correction is negligible in most bins, you don't need to fit for it separately. And then if you sum the detection significance cumulatively across all the bins, then these are our forecasts for SO crosswise and CMB-S4 crosswise. For SO crosswise, it's order of 100 sigma. For CMB-S4 crosswise, it's 200 sigma. And I know these might look like a lot, but even with the KSE squared estimator, which I show in the final column there, even with that, if you do not restrict, even there, if you do not restrict the galaxy modes and you include nonlinear modes for the galaxy field, you expect a high detection significance. And in the middle, I'm showing the detection significance for the extended case where we do not restrict our galaxy modes. So basically, by comparing the last two columns, you can see that you're gaining in signal to noise ratio when you take a full 3-point function instead of just taking KSE squared across galaxies. And then here we can even choose to restrict our galaxy field to linear scales and still get a very high detection significance. So yeah, as I said, right now, as you go from ACT data to SO data, the detection significance for this estimator is going to go up by a lot. And as I mentioned earlier, because you are not using the nonlinear galaxy bias dominated modes, it gives you better control over those uncertainties. And the other advantage of using this sort of bin bispectrum method is that we haven't derived any optimal weights to construct this bispectrum. So you do not need to assume a theory template to detect the signal and data, basically. And I can go more into that if there's any questions there. So as it is, just by detecting the amplitude of the signal, with SO data, we can potentially probe the baryon abundance and possibly also the gas density profile, although there's more work to be done here to get that out of such measurements.
What SNR would you get with just ACT?
So with ACT, it's going to be around 10, 15 sigma, something
So
like
you
that.
could already do this analysis with ACT.
Yeah,
Or
so
like
this method could actually be used in ACT
Are you
data.
gonna use it or?
That was one of my planned projects, but it's basically before jumping to and doing this in ACT data, we also want to test this in SIMS. Also, even for the existing KSE squared method, there are a few things that need to be checked in SIMS before actually doing the measurement, because one is just checking for this, because we need foreground clean CMB maps, we have to be careful about any residual CIB and stuff. And in our forecasts, we actually use the post-ILC noise curves, which can have, basically the post-ILC maps can still have some residual programs. So we have tried to account for that in the forecasts, but in actual data, it's complicated. So basically, we are planning to do this measurement with ACT data. There's just a couple of steps in the middle that need to be
Like
done.
forecast versus real data.
Yeah, so this
Good
is
story.
more like, because we are proposing a new technique, we're just saying that this is the kind of detection significance that we can expect. And aside from getting information about the gas density profile or the abundance of baryons, as I mentioned earlier, we can also use this as a cosmological probe. Now, as with any KSE statistic out there, your inference is limited by this degeneracy between how well you know the baryonic astrophysics, and that dictates how well you can constrain the cosmology. And that can be taken care of in different ways depending on the estimator. In our case, we include a free amplitude as a nuisance parameter, sort of, to account for the uncertainty on the baryonic astrophysics side, or how the gas is distributed. The rough amplitude of the signal scales as sigma to the power 6 or so. And because of the scale separation that I was mentioning earlier, we expect that cosmological signatures which dominate at quasi-linear scales could be more robustly constrained using this new bispectrum. So one example would be constraining the sum of neutrino masses. So as is pictorially shown over there, depending on what the sum of neutrino masses is, you expect differences in the clustering of matter in the large scale structure. And our KSZ observable in particular is dependent on the sum of neutrino masses in two ways. One, neutrino masses suppress the clustering of matter at small scales, but they also induce a scale dependence in the linear growth rate that I mentioned earlier. And because velocities are proportional to this growth rate, they imprint our KSZ observable. So we did initial Fisher forecasts for ΛCDM plus the sum of neutrino masses and a nuisance parameter for the astrophysical uncertainties, which scales the overall amplitude. And these are the initial Fisher forecasts that we got. This is an MEV for SO crosswise. For both of them, we get around 100 MEV. And here I've only assumed a primary Planck prior. There is no other prior applied. So there's no PAO prior or lensing prior applied here. So yeah. This is just the conclusion slide. We have proposed a novel projected fields KSZ bispectrum, which does not require individual redshifts of galaxies to detect the KSZ, which means that it's also applicable to all kinds of other large-scale structure tracers. And it improves upon the existing KSZ squared method in a few ways, as I mentioned earlier. And we expect very high SNR with SO and eventually CMB-S4. And again, you can use LSST galaxies in place of WISE galaxies to do these sort of detections. And we demonstrated that this could become a complementary probe of neutrino masses. Potentially, you can also constrain dark energy with this through its dependence on the growth rate. And yeah, in terms of next steps, one is just modeling the dependence of the baryon density profile on this overall KSZ signal more accurately. The way this would be done would be in a halo model sort of framework. But that is my immediate next step before we actually move on to data. Yeah, thank you.
Did you consider the leakage from lensing?
Yeah.
Will mess it up also, right?
Yeah. So basically, so the theoretical model that we have, you assume unlensed CMB when you derive those terms. But then because your CMB is lensed, you will pick up a lensing correction. So in the paper, I've actually derived the expression for what the lensing correction should look like. It's not zero, but it's negligible in most bins in our case. So it's not exactly zero, but it's negligible. The reason it's significant for the KSZ squared estimator is because they also they have a Wiener filter that needs to be used to do the squaring of the CMB map, and that's basically what leads to a more significant lensing contribution in that case. Here, it's effectively like a remapping of the CMB, the primary CMB. That's roughly the effect that lensing has.
But you can have cross term, right? KSG cross ratio lensing plus KSG cross CIB, and those cross terms can enter into this estimator, right?
Yeah. So as for CIB, we are assuming that you're starting with foreground clean maps. If you have any residual CIB, that will be an additional contribution which you should account for. But like that could be checked maybe by using this CIB deprojected CMB map. Like you could check how much residual CIB is contributing maybe by doing that. But the lensing, the CMB lensing effect itself is captured in the lensing correction, and it turns out to be negligible.
So the lensing correction is like the like you're building some kind of optimal estimator, is that right?
No.
You said you don't have any weights, that's the thing.
Yeah,
that you
so
got.
here, instead of deriving like a optimal bispectrum with like optimal weights,
Yes,
we're just doing this bin bispectrum
okay,
sort of a technique. So yeah, so you're not assuming any,
but if you had
like
actual
you-
data, you would
yeah.
have to weight the data with some weights, no?
so the weights would be in the bin bispectrum, the weights would be the number of modes that you have for each triangle. Roughly
But
speaking.
isn't there like a, no? Because your data is just the CMB temperature, like you cannot separate KZ from the primary, right?
Yeah, that's why we're
So you
doing
take
classes, yeah.
you take like T of
Yeah.
L1 M1, T of L2 M2.
Yeah.
Times delta galaxy.
Yeah.
Of
Yeah.
L3 M3.
Yeah.
And you have to multiply this by some function of L1, L2, L3, right? Isn't that like, don't you multiply it by your expected bispectrum?
No. No, I mean, when we actually want to infer anything, you
Yeah.
have to infer with theory, but no, it's not like the optimal estimator sort
Okay.
of a approach. And yeah, we had some discussion about, I think we also had this discussion briefly earlier. We could derive like in the squeeze limit where we see most of the signal, we could possibly construct some sort of an optimal estimator in that limit, maybe. One sort of factor that for not doing that is that the distribution of gas there's still uncertainties on what the gas, how baryons are distributed. And we haven't accounted for that in these initial forecasts, but that will impact the overall signal. So if you derive the optimal weights assuming some gas distribution and the actual gas distribution is different, then there could be a bias that would need to be accounted for, basically. Here, you can, if you just take this sort of a formalism and you apply it to real data, just to do a detection, you don't need to assume a theory sort of template to do the detection itself. That's my understanding of it, yeah.
Yeah, what you were calling KSE squared measurement, that at the start you mentioned 3 techniques: pairwise KSE, velocity weighted stacking, and velocity weighted reconstruction. This KSE squared, is that one of those? Or
No, that's not equivalent to all of those.
Okay,
Yeah,
so what?
Yeah. So the KSE squared, again, I worked on the KSE squared estimator in my previous project, but
Oh,
that and this, they are different because they use projected fields of galaxies. So you're not using.
the KSE squared also uses a projected field.
Yeah. So it's like KSE squared crossed with the projected galaxy.
That's
field.
right. That's
Right.
what motivated the square, was
Yeah.
because when you project it goes
Yeah,
to
yeah.
0.
And
Okay.
I added that slide just as a sort of clarification because there's many different KSE detection techniques
Yes.
out there. But what we are doing is not mathematically equivalent even to what they are probing, basically.
So here's like one temperature, one CMB field, and then 2 galaxy fields.
Yeah,
These one
that's-
versus your method is two.
TTG. Yeah, so
CMB
roughly the way we talk about that is these are the 3D tomography methods. They are equivalent to TGG,
Right.
one temperature map, 2 galaxy fields. And what we have is TTG. So
It's separate.
the underlying statistic that you're getting is also
And
different.
it is higher SNR what you have.
I mean, even with these other techniques, the SNR will go up with SO data. But
And
Yeah.
so
yeah, it's also
holistically, shouldn't one just take the best combination of all these techniques?
Yeah,
in
so
some
because
sense?
there's all these techniques, like even these, which are mathematically sort of equivalent to each other, which one you use depends on what you're interested in constraining.
Mhm.
So for example, this velocity weighted stacking method, that's really like ideally suited for measuring the the gas density profile. And recently in ArcData, like few months ago, actually even this month, there was a new measurement with DESI galaxies, where they did ACT plus DESI. This time they used the spectroscopic galaxies, but basically, this technique, for example, is very ideally suited to do that. It does this sort of aperture photometry kind of thing, where it stacks the different clusters. and assigns different weights to overall get like a statistical measurement of the gas density for all those clusters. So which technique you use depends on what you want to constrain. And different techniques have different advantages. And the second factor is what data do you want to use from the landscape structure side, basically. As I mentioned, this technique, for using projected fields, you can replace galaxies completely with lensing convergence, and the same formalism should work. There will be different systematics which will need to be accounted for each of them, like even 21 centimeter would get, like you'll have to worry about other things, I guess, but the basic formalism will work. The basic technique will work. Whereas these ones, they are not applicable to those data sets. Yeah.
Okay, thank you again.
Okay.